All right, welcome back, everybody. This is the 2022 Virtual Residency Workshop. It's Tuesday, early afternoon, June 28th. Our next speaker is Jerry Perez from University of Texas at Dallas, and he's going to talk about the structure of a cluster supercomputer. So take it away, Jerry.
Thank you, Henry. So I'm going to try to get as much interaction with the audience as possible. I know not everybody has a cluster, and I know some people might have some questions as to, what do I need to do to get into clustering? And there are some answers to that. Sometimes it's make your own, sometimes it's use somebody else's, and sometimes it's in between. So with that, let me introduce myself. I'm Jerry Perez. I am the Director for Cyber Infrastructure Operations at UT Dallas, and I also teach in the Business Graduate School. I teach big data analytics and machine learning. So today we're going to see some just very basic configurations of clusters, not really into great depth, just enough for people to get an idea of what a cluster is, and also what kind of types of clusters are out there, and also what's on the horizon. What's out there that that we hopefully will see as a normal practice within HPC. Okay. So what is a supercomputer? So we're going to answer this question time and time again throughout today's talk. We'll talk about some examples. There are examples, and of course the age-old question: why? Why are we even doing this? And so we'll have an opportunity to discuss that. Let's see here. And if you have any questions, I will open up the chat on my side, and we can share what we know. And so if you have any questions, I'll be happy to talk about it. Of course, we'll have a Q&A at the end of this, but if there's just something that has to be shared, please, by all means, share it. My machine is being a little weird. So we have some HPC challenges that we're going to talk about today. They're pretty standard, such as what are we doing on supercomputers, such as simulations, parallelism, how are we going to share memory and processing, and then we'll talk about the cluster components themselves. And I'll try to use some of what we use here at UTD as an example. I'll try not to go too much into depth because that's not the point of today's talk. Today's talk is just an introduction so that administrators or thought leaders within organizations, if they're thinking about clustering, this is a really good talk to look at, because then this should give you like a 40,000 foot view of what an HPC cluster is and what you can do with it, and the different options that you have. Okay, so we're also going to talk about a little bit about design, and we'll have a brief discussion on that. I will share how we do the deployments out at UTD. Back in the olden days, we used to just write batch scripts, or we would do it by hand, so to speak. We would have a host file that would have all the hosts and their MAC addresses and their IP addresses predefined, and then we would use scripting to install the cluster software. And that would be nowadays we're using better tools, and so we'll talk a little bit about that in just a minute. We also talk about performance. As you know, I've been in supercomputing for about 20 years, and so from the very beginning, it has changed dramatically. Our first computers were a bunch of beige boxes put together on a metal rack, and it was a Beowulf cluster, and it wasn't made by anyone. It was made by us, at the center, and so it didn't have any of the high-speed interconnects that we have today. It didn't have huge processors with multiple cores, it was just a basic beige box. So performance was definitely something that we needed back then. And as time progressed, the vendors developed a good infrastructure for many years. I worked with Dell, and we had a chance to put together a couple of clusters, at least 4 of them. And I saw the performance change dramatically with each iteration. So we'll talk a little bit about that. And we'll also talk about some new technologies. Quantum computing. This is something that I've been looking at for the last 2 years. And it's a little nebulous because it doesn't operate the same as a traditional computer. So you have to have a few extra sets of understanding, such as the understanding of gate logic, the understanding of physics, and basically able to transcribe that knowledge over to classical computer science, where in computer science you have your algorithms and your methods. In quantum computing, they have similar but not the same type of attributes. So there has to be some happy medium, and there is, and I'll share that today, how we are taking classical computing and converting it over to quantum computing. So we'll look at that. And then we'll talk about Exceed. As you know, it's at its sunset phase, and so it's about to set. And we'll also talk about Access, which is the new program that's coming up. They'll have at least 5 years in that program. So we're going to have an opportunity to talk a little bit about that and look at that, not in too much detail, but just enough to understand, what's in that program. So at UTD, my department's called the Cyber Infrastructure Research Computing, CIRC, and it was established in 2015. And what it does is it serves the campus with the following clusters. We have a general compute cluster called Ganymede, and I'll talk a little bit about its history in just a minute. It's a PI-funded general use cluster. Everyone can use it. It also has a condo model, so that if people need specialized hardware, specialized usage, they usually purchase that, and then we can install that into the condo. Europa is an NSF-funded research cluster, and its primary purpose is going to be to share computing power with the other universities within the UT system that are part of the grant. And its purpose is to facilitate computing for outreach. And so it's going to help researchers at these institutions, but also help students, especially students who are minorities. And also it's built to serve minority serving institutions. And so Europa has a very interesting mission, and it's going to be a very interesting tool to use for outreach. And so that's what Europa is going to be used for. And then we have another cluster, Titan, which is GPU. And as you know, GPU is used for a lot of interesting machine learning operations, a lot of graphics processing. So a lot of these GPU-based applications that are out there is what Titan is suited for. Okay. So at UTD, what we do with our clusters is we deploy using Ansible, and the software that we use to manage the cluster is called OpenHPC. So the basic cluster architecture head node is here. And as you can see, the Ethernet fabric for management is here. It's a parallel file system for storage. And we have an MPI fabric, which is InfiniBand, or you could use OmniPath. And we also have Ethernet only. And then we have compute nodes as well. And so what we do is with the Ansible, we have something called a playbook. And what the playbook does is that it defines the basic software stack of each device that's going to use software. And we can be very selective as to what we put in the software stack. And we can also be very precise. And so each of these playbooks can serve a role. Okay, so I have an example of that here. So one particular role is, for example, the cluster front-end deployment. And so it used to take a couple of hours to set up a cluster front-end by hand. I did it a couple of times, but now with the Ansible, it takes less than 15 minutes. And so you basically have your predefined software. You have your Ansible playbook ready to go, and you install it through a boot process. And it detects, when you put Ansible on there, it will then start reading the playbook and then start the installation. Very nice, it's very automated. You can also use Ansible for creating virtual machines. So we do have those here on campus, and we have several of them that we use, especially for lab notebooks, like electronic lab notebooks. And also we've deployed our file server configurations using Ansible. And we also use Ansible to add users. So it's basically just like redeploying the cluster, but we're just adding users to that particular part of the installation. We also can make changes to deployments by adding and removing services. And so this makes managing clusters a lot easier and more efficient. So, and if any of you all are interested in automating your installations after the meeting, please let me know. Let's see, there's some questions here. So can you share your Ansible playbooks? Absolutely. Is there a reason why we use Ansible rather than Puppet or SaltStack? Well, I think Ansible crossed the finish line first. It was actually something that we all discussed almost 3 years ago. And so we decided to dedicate the cycles to getting to know Ansible the best. And we also used it within our own division. Within OIT, Ansible is used in different parts. So it makes sense that we're using the same application that the other parts of IT is using, right? I mean, we could use Puppet, we could use SaltStack, but we're recreating the wheel several times, but we already have other people, other organizations within IT that use Ansible. So it makes sense, right, that we use it as well. Okay, but yes, Vinod, get with me after the talk and I'll be happy to share what the playbooks look like. Of course, we don't have any confidential information. These are all just general installations. And of course, I won't share any playbooks with user information in it, but yes, I can show you about the cluster setups and things like that. So there are some research examples that we do run within our clusters. We have geophysics, molecular dynamics. There are also spatial simulations, and of course, big data. So what type of applications do you all run out there on your supercomputers? Do any of y'all have anything off the top of your head? Anybody? Okay, MD, chemical flow dynamics, genomics. Genomics are machine learning lamps. We have 100 modules installed, anything and everything. Jupyter notebooks, and we'll see that again, by the way. Jupyter is very neat. You can do a lot of things with that. Large scale graphs, MATLAB. Of course, everybody's doing MATLAB in our studio, right? Statistical analysis, yes. So it looks like we're all pretty much on the same page then. We definitely need to have supercomputing, and these are the applications that are running on these supercomputers. And I don't want to say it's fairly common, but it is fairly common that all these things that you just listed, Kubernetes, that's a good one. A lot of these applications are run across many other supercomputing centers. And this is pretty much the state of research computing. It's almost a given that everyone's going to run R, everyone's going to run MATLAB, everyone's going to run some form or fashion of data analytics. Let's see here. And then Chris says the astronomers compile their own, like Athena or Cactus. Yes. So we do have some specialized installations, and we allow them to run them. There's no problem with that. We just have to get all the pieces that we need from the PI, and we can put it together for them. So here's a question. What is a supercomputer? Well, it's a computer with very high-level computational capacities compared to general purpose computers such as a personal desktop, laptop, or cell phone. I don't know if any of y'all recognize this one. This was taken at TAC. Oh yeah, top 500. And so this was Stampede 2. The interesting story to Stampede is when they retired Stampede, what did they do with it? So that's a big question people ask. So what do big supercomputing centers do with their aging older hardware rather? And so you have this huge supercomputer. Well, part of the Ganymede story is that we inherited it in 2015 and we repurposed it. And so what you're actually looking at here is Ganymede's previous life. And it looks just like this, with the exception of those look like blowers on the side, but we have the compute part as well. Let's see. So Ganymede is named after Jupiter's largest satellite. So it's a cyber infrastructure research computing cluster built on the condo model, like I said earlier. So while Ganymede does have free to use queues available at all UT Dallas researchers, a majority of the computational power is provided by nodes purchased for exclusive group access. Okay, so let's talk a little bit about our queuing system. Well, we have a debug queue. It only has 2 nodes, and you can only use it for about 2 hours. And the whole point is so that you can test your application on the debug queue. We encourage our users to not run on the front end. Every semester, we always have a few. So that's why we have a debug queue to allow people to do their testing. And then we have a normal queue, we have about 110 nodes set aside for that. And we have a maximum runtime of up to 4 days there. So that's where the majority of the work runs on the normal. And then we have some specialized queues. We have a small memory queue where if people need to run many small jobs, but they're not memory bound, then it's a perfect queue for them. And then we have some other queues where the memory incrementally increases. So we have a 96N, which stands for 96 gigabytes, and it's also an Intel Nehalem. We also have a 128S, which is a 128 gigabyte nodes. So, and it's Sandy Bridge. And then we have 156H, which it's one huge Haswell, and it has 256 gigabytes. And so what this does is it gives users the ability to be able to run jobs that require more memory. And so these are more specialized. And of course, these are general use nodes. So what does that mean? It means that we have a lot more compute capacity. It's just that in the form of condo nodes that are owned by research groups, they're owned by PIs, and their capabilities are a lot better than what you see here on the general queue. But we have too many to list right now, so I just wanted to keep it just very basic, very general. So here's, yes. So remember, I told you that we had inherited some older hardware, but it's all working and it's useful. So there are some questions, so let's go through them real quick. You guys type real fast, by the way. So first question was, any reason all Intel and no AMD? Well, this is what was given to us. And so the majority of these nodes came from Stampede 2. So of course, there won't be any AMD in this iteration, but I'm certain that we may have some in the condo. Are the research nodes made available to the general use if not in use? On some occasions, yes, but what we do is we will talk to the PI and we'll ask them real nicely if we can. So on occasion, we've been allowed to use PI resources, but again, you have to approach the PI carefully and make sure that they're not running anything or if there's any deadlines. And of course, we have to watch those users who are borrowing PI condo nodes because there is that possibility for abuse, and we don't want that, right? We want everybody to be happy. So if we do allow people to use it, we'll make it clear what the time limits are that they can use. So we actually find out what the requirements are, just like you would a new user, right? From the PI support talk, you basically find out how much processing power the application needs, how much memory does it need, how much storage does it need, and how soon do they need to use the resource. With that, then we can turn around and go to the PI and say, could we borrow your resource for this amount of time? And I've not been told no yet, but again, we have to be precise and clear as to how much, how long the resource is going to be used for, and that's important, right? Because if we just give people just carte blanche access, then the opportunity for abuse goes up, right? So that's the answer for CJ. Let's see. So what was available to be recycled? So you're talking about the original Stampede, I take it. Well, basically, we were given the original compute nodes, and we were even given the first iteration of Corral. I don't know if you all remember Corral. It was a storage system out at TAC. The issue with inheriting someone's storage system, especially if it's a DDN, is once a DDN system goes out of warranty or out of support, DDN will not support it. And so it was a lemon, the storage part. So we didn't put it into production, but the compute part we did. So we did recycle Corral, but the compute we still have going on. So we haven't recycled any of it. And surprisingly, it's been running very well. We've only had maybe, I want to say tops, maybe 5 or 6 nodes fail for various reasons. Other than that, it's been running very good. Let's see here. Can your non-condo researchers use spare cycles on condo nodes? Jeff, yes, they can, but we have to ask the PIs nicely. Let's see here. Other questions? Chris, we sold our retired cluster to Georgia Southern for $100. Okay, that's okay. That's really good to know. And you see, and it's good because it gives people at least a way into HPC without having to drop a huge amount of money into it. It's perfect if you can do that. And I think that's where the Trekkies project really comes in handy, with Europa, giving people access and getting them used to using high performance computing resources, so that maybe at some point they will dedicate time and money to a cluster of some sort. And some of these smaller institutions may be a good fit for some of this retired cyber infrastructure that you're talking about. Let's see, I have a couple more questions. Can you, okay. Is there an accounting or recharge in place? Let me see, someone just sent another message, it knocked it out. Give me a second. Okay, Luigi says, we still have some Sandy Bridge. A single AMD EPYC node is faster than 8 Sandy Bridge. At some point, power and AC usage tilts the cost equations to buying EPYC and retiring old cores. That's true. In fact, we were in a situation when we were at a colo. We had to pay for power and cooling, and we had to watch our power consumption. Because if we went beyond a certain level, then it would take us to the next tier, which is more expensive. So I completely agree with you. That's power and cooling is a hot topic, pun intended. We also use preemption to cycle harvest condo nodes, and that's the cost of hosting in our data center. Yes, I am aware of that method because some campuses do that. The campus I came from before UTD did that, we would cycle harvest the idle cycles. And then what we would do is we would make the PI owners of that infrastructure have priority on that infrastructure. And so basically, we would ask people to checkpoint their jobs, especially if they're long running jobs, so that if the PI owner needs to use that resource, that job that's running that doesn't belong to that user, well, that doesn't belong to the PI, rather, goes to sleep. And so then the PI can then, and that PI's research group can then use their own resources. And then once they're done, the other job wakes back up and finishes. So yes, that is something common that's used. Okay, what else? Brad says, I keep reminding people the old hardware still does what it did when we bought it. A lot of life in those old boxes. Thanks, Brad. We totally agree with you. But the good news is that these older the older hardware is a great pump primer for the new hardware. We've already demonstrated that we can run a center, we can serve a campus. So the next step is to use that synergy and use that momentum to get more resources. And on that, we are. So the PIs are very pleased, and so they're willing to invest more in the infrastructure. And so we have over $1 million worth coming this year for a refresh, and that should be happening rather soon in the month of July. So it's good. All right, so let's move on. Good questions. Thank you, everybody. So why supercomputing? Well, we use it to resolve tomorrow's problems today. Normally, these problems can't be solved on your desktop. They can't be solved on your laptop. And so we have to have an infrastructure set up so that we can solve these larger problems. And there are several ways to do it. But if it takes a long time to run, so it may be time dependent, we can set up nodes for that. If it's something that's parallel and that we have to process it parallel, and we'll talk about that. There's two types of parallelism. We can do that as well. So with that, the cluster HPC helps us bypass the limitations of Moore's law, because as you know, you can only shrink the semiconductors only down to a certain size until you reach a limit, and so we can't double our compute capabilities anymore like it used to. So what we do is instead of making chips smaller and faster, we just add more cores, or we add more computers, right? So it's either more cores or more computers or both. This idea actually was brought up many years ago in the 70s by a person named Admiral Grace Hopper. She's actually the grandmother of big data, and she also helped write the COBOL programming language. And so she addressed Moore's law by saying, hey, we shouldn't be making so many high performance computers per se, but we should add more of them and have them run parallel or in series. And so she had this idea, which actually sparked this whole idea of clustering, this whole idea of using many computers to create one virtual supercomputer. So Admiral Hopper gets the credit for that. But supercomputing also allows us to increase the research outcomes and by orders of magnitude by manipulating excessive data points and through machine learning. And so not only does the compute improve, but our storage capabilities have improved. You know, when I first started in supercomputing, our first hard drives, you know, they weren't even a gigabyte. But now we're talking about petabytes of storage now, and it can be shared across campus. So a lot has changed, and so we have a lot of growth that has taken place. And so I'm really happy to share this because it allows us to, you know, solve expensive and dangerous problems in our simulations, and it also allows us to answer a lot of difficult problems that normally you can't process on a normal computer. So I saw this evolution from many years ago until now, where we had to wait literally for weeks in order for a calculation to finish. And there were times when we lost power, there were times when we lost a computer node, and the jobs weren't smart enough to recover. And so it was very unfortunate. Or hard drive failures. The first hard drives were terrible. And so you want to talk about angry customers. 20 years ago, high performance computing wasn't fun. But things did get better eventually. Let's see here. Here's a question from Phil Boarding. So what kind of support do you provide for visualization of outputs? So you're talking about like taking data and visualizing it. Is that right, Phil? Or taking the data and creating a graph output? Phil? Okay, we'll get back to that at the end of the talk. So what are the HPC challenges? Well, we have a couple of challenges really, and they're realistic. One is staffing. So we need to have people who have a broad experience in IT, but also have a knack for research, who feel comfortable talking with PIs, comfortable with different sciences that go beyond perhaps their understanding. So what I had to do as I was going through my earlier career was I had to learn pretty much what the customer was doing. I had to meet them halfway. So I knew how to run things on the cluster, but they knew what their science did. And so what they wanted was to get their science running on the supercomputer. But in order for that to happen, I had to understand what they were doing. So I learned about bioinformatics. I learned about molecular dynamics. I learned about statistical analysis. Learned about chemistry, computational chemistry. And I learned about physics. Especially if you all remember the Atlas project. I worked on that for a couple of years. That was interesting. So you have to be willing to go outside of your comfort zone as an IT person, especially in HPC, and be willing to meet the PIs halfway. And this is part of the whole PI support paradigm. And that is, we know what we're doing in IT, but they have an idea of what they think they know. But our job is to bridge what they know and what we know into production. And so, and of course, we have to test. We have to make sure that what they're asking for is correct. So we just can't assume, well, just because it's running, it's going to work. So again, we just can't throw them at the cluster and then walk away. we have to help them, especially if it's a new app or if it's a new customer. We have to make sure that their job's running correctly and that their output is correct. Okay, so we have to have staff that keeps that in mind. We just can't fire and forget, so to speak. Once we've figured out somebody else's problem, we then assume it's done. We can't do that. So we have to teach that to to the people who work in HPC. But also with that, the thing I like about HPC though is it welcomes people from many walks of life. You'll see that not many people have like degrees in computer science or even IT type degrees. The people that I've worked with in the past had degrees in mechanical engineering, physics, chemistry, mathematics. My old boss was a math professor. He directed HPC for almost 30 years. Yeah, so the thing I like about HPC is it has a very large umbrella for many disciplines to be under at the time. And yes, William, it can be a steep learning curve if you don't have documentation. Documentation is key. Ever since I got here, I've been hammering the whole documentation hammer. We have to also have SOPs, and we also have to have service level agreements that clearly define what is it that we do for a particular customer at a given time. But also SOPs, standard operating procedures on what we do on an everyday, doing our everyday jobs, looking at, the resources that we take care of, making sure that that the queues aren't overwhelmed, making sure that the storage isn't full, things like that. But the key is documentation. And so we'd have to have, if you're going to have an HPC center, you have to have two things. You have to have documentation for your users to teach them to be good users. And then we need to have documentation for our support staff to help everybody understand, well, what do you do when something fails? What do you do when you want to erect a new storage system? Or what do you do when you want to add new resources to a system? These are questions that have to be answered in documentation. And with good documentation, that learning curve gets more level so that everybody's on the same page. As far as costs go, creating a supercomputer is expensive. I've actually lived through two brand new purchases in my career, and they are very expensive. They're amazing to see once they're put together. I don't know if any of y'all ever remembered like the Atari 2600 or the Commodore 64, and you opened it up on Christmas and it has like that really fresh plastic smell. Well, that's what a brand new supercomputer smells like. It's an amazing experience. So I think it's really nice to be able to have the resources to get a brand new supercomputer, but just know that if you're going to do it, it is expensive. So that you're going to need buy-in on everybody from your IT leadership all the way up to the president if you're going to do something like that. There are several ways to do it. It's just, again, it takes building relationships, and it took many years. So at Texas Tech, when I joined in 2002, we bought our first brand new one in 2008. So it took 6 years of greasing the wheels of politics and just getting people on board with the mission. And eventually we did get the money for that, but we had to convince literally everybody who had a budget on campus to invest in high performance computing. And then after that, in 2018, a brand new system was purchased again, and it was close to $4 million. And it was it's called Quanta, and I think there was another system called Heta Lacona, which was like Quanta too. It's a great system, but again, brand new. They're very, very expensive. But I'll never forget the brand new computer smell that these things come with. It just reminded me of unboxing my Atari from the 1970s. It just blew me away. So now that you've got a system, what do you do with it? How do you take care of it? Well, you've got some questions to answer, such as support equipment. What kind of support equipment do I have in my center? Do I have PDUs? Do I have UPSs, which goes into power? Do I have enough power to maintain this equipment? Do I have enough power to grow? So that was one of the problems that we ran into, not we as an UTD, but I ran into in the past was we would buy new equipment, but then we'd have to turn off old equipment in order to run the new equipment because we didn't have the power. So one of the last things I did before I left Texas Tech was the power upgrade. And so I worked with Vertiv, and we upgraded the center to, I want to say, over 2 megawatts. And so there's more than enough in there to power everything. And also you have space, because not everybody has a Walmart-sized machine room. You have to take care of that space, and you have to jealously guard it, and you have to manage it, because that space, you know, is limited and it's very valuable. Machine room space is very expensive. And then cooling, you've got to be able to keep everything cool. There's a formula that you can use to calculate, you know, how many tons of cooling do you need, how many BTUs are in the room. So hopefully all these questions get answered before you buy anything, before you even put anything on paper. Get all this calculated, and you can have your facilities people help you with that. I mean, the formulas aren't that difficult, but it's good to have a certified engineer there with you to help back up your calculations, and also to just be an extra sanity check. So when you're designing a machine room and you're deploying in a machine room, it's a team effort. Even though, yeah, we can all Google the formulas and then measure the room, measure the temperature, it's better to have your university engineers involved, especially the ones who work in facilities management. Okay. So here's an example of a simulation. One of our very important users, Professor David Lumley, he works in seismic simulation. And so in this simulation here, this program attempts to reproduce an abstract model of a particular system. So as you can see here, there's a before and after picture. And what he does in his research is he wants to develop a system that will help rescuers locate buildings that don't exist anymore because of a disaster, whether it's an earthquake, whether it's a tornado or a flood. Using this type of technology, he's able to reconstruct what used to be there. Even after the earth is moved, he could then create maps and give them to rescuers to find people, and also just to look for buildings. The other interesting thing is this technology can also be used to find very old cities that no longer exist, you know, like cities from many thousands of years ago. So this is a really neat use of the supercomputers here at UTD. Okay, so we spoke a little bit about parallelism and how it functions within a supercomputer. So performing the computations in parallel, they carry out many calculations simultaneously. They utilize thousands of general purpose computers all working together to solve the same problem at the same time. So this is an excellent use case for how our modern supercomputers work. But there are different types of parallelism, right? You have multi-threading versus multi-processing, whereas in multi-threading, we're more interested in sharing memory. And in multi-processing, we're looking at using the distributed parallelism in processors. So one is using memory because it's a memory-bound problem. It needs more memory. And then if you need more compute, especially if you're trying to brute force a calculation, then the distributed parallelism in the processes will be the optimum way of doing that. So that's a little talk on parallelism. So let's talk a little bit about the design. So we have some cluster components. We have compute, we have networking, we have storage, we have the batch scheduler, and we have high performance computing software. So compute, and see, I always joke about this, about the blades that we have. I call them the pizza boxes. Well, in this picture, it's an actual pizza box. But in compute, you can have CPUs, you can have GPUs, memory, interconnects, and we'll talk a little bit more about those. And then you have options, right? Does the node have disks or does it not have disks? Is it stateful or is it stateless? So this is pretty much the outlook, the layout of a compute node. And then we have the network interconnects. And of course, I'm not advertising for Mellanox or anything like that. This is just a nice picture. But there are other technologies that are out there, newer technologies. But let's just talk a little bit about what's out there right now and what we have here. So you have some factors to consider with your network interconnects. And so I guess one question is what are interconnects used for? So interconnects are used for moving your data and your compute across the nodes to each other so that there's communication. And the faster the interconnects are, the better the communication works, especially in parallel, like MPI. So there are some factors involved. So you have InfiniBand, and it has a low latency. Its speeds are anywhere between 1.5 microseconds through less than 0.6 microseconds. And I have a neat slide that shows the evolution of that and how it's improved. With that, cluster interconnects can go as fast as 400 gigabytes per second, as low as 40 gigabytes per second. And then there's Ethernet, which is the standard networking that we pretty much all use at home. The Cat5 cable, this thing here. Basically, it has low latency, usually 12 seconds through 1.5 microseconds. But that technology has been improving as well. In fact, it's starting to challenge some of these more expensive InfiniBand interconnect fabrics, and you'll see that in a minute. But the data management is primarily for if we need to do any kind of administration, system administration work, where we're on the command line and we're investigating, say, a node failure or a job failure, then we would communicate using this Ethernet network. So, and we don't run production on that. Okay. But basically, the speeds have improved dramatically from 1 gigabyte per second up to 100 gigs. But the communications, there are now 10 gig and 400 gigabyte Ethernet connections. And again, the technology is starting to challenge the InfiniBand. And so I have a slide here that demonstrates that in just a minute. So the InfiniBand, let's talk about how it's improved. So we have several types that have been used in the past. The first were the SDRs and the DDRs, and then the more advanced were the QDRs and the HDRs. And you can see here in this example, let me see, you should be able to see my little pointer, where it's evolved. And we have the next generation NDR, XDR, and GDR. And just for a single link, you have up to 100, 200, and 400 gigabytes per second, which is very fast. But then what you can do is you can add more links. And it looks like this topology allows us to go up to 12 links. And depending upon what you're doing, so like in a standard cluster, one is enough. But for like a let's say it's a front end to a cluster, then you'd probably do like 4 links, or the center of a storage hub would be 4 links. But then if you're going to do like a wide area network or a city area network or a what do they call it, a metropolitan network, then you would use these really large links. And as you can see, the speed goes up dramatically, especially with these newer technologies. They have, I think at the top, 4,800 gigabytes per second. So the technology has definitely gotten better, and you can see the evolution, right? Because this is by year, because I can actually remember these technologies that were used at the High Performance Computing Center back at Texas Tech. I remember these, but then now we're using, we have some HDR, I believe, here at UTD, but then the NDR, XDR, and GDR, it's changing the game. I mean, it's dramatic compared to what almost 20 years ago. So 20 years ago, we were at 24 gigabytes per second, and now today we're at 4,800 gigabytes per second. So definitely InfiniBand networking has improved dramatically. So that's the good news. The bad news is I don't want to see the price tag to any of this stuff. I'm certain it's going to be very expensive, but if you need it and you can get it, then that's wonderful. Because again, the technology is it's very good with how far it's gone. You know, in this time period, in 20 years, you can literally see how networking has improved just by watching the numbers go up from left to right. Okay, so Ethernet. Okay, so Ethernet itself has improved tremendously. And of course, it has its uses depending upon how much you need in automation, such as buildings and smart devices, Internet of Things. A lot of these are beginning to get to the stage of where 10 gigabytes per second is the norm, and everything communicates wirelessly, communicates along a network wired network, and it's actually high performance in its own right. And then our own vehicles have their own local area networks, where you have some vehicles that have a low end of 10 megabits per second, and then you have 10 gigabytes, and then up to 100 gigabytes for a local area network for a car. So again, you can see how the Ethernet technology has improved. And for us in our high performance computing centers, they have Ethernet that can go up to 400 gigabytes per second. And this is generally where the supercomputer would live, in the server in the switch room. So this is something that we can look forward to, because this also brings down costs, especially for networking. So hopefully the InfiniBand folks are keeping an eye on this, that Ethernet is coming really close to eating their lunch. So that's something to consider, especially when you're designing a cluster. And then we have co-location and mobile fixed. So these are for the service providers. And if you see here, you can see how much networking has evolved incredibly so. They have up to 1.6 terabytes per second networking. And again, we're talking about like the backbone to the internet, things like that. But imagine this performance just existing in a building, existing in a co-location central office or a branch office. So again, networks are getting faster, they're getting more efficient, and because it's Ethernet, they're getting cheaper. So this is something to keep an eye out for. And then for cloud providers, again, the news is very good, because the networking is getting better. It brings down the cost of cloud. It brings down the cost of all this here. So where is latency on newer Ethernet? Well, that is a good question. I actually have that back here. So the Ethernet latency is about for the high-end Ethernet, it's about 1.5 microseconds, even though the standard Ethernet is about 12 seconds for the low-end stuff. But for the faster 100 gigabyte or 400 gigabyte, we're talking about 1.5 microseconds, which in itself is great. And has the packet overhead improved? Well, it's going to have to have improved, especially if throughput's improved, right? So I think that's a given. So that's pretty much it that you really need to know, and that is both of these network fabrics have improved over time, and the cost should be going down because of that. And so I think it's a great time to start thinking about getting into HPC, because that's just one part that I think we can control the costs by selecting the technologies that we have here in order to have a functioning cluster. But if you want to tweak the cluster to do special things, then that's where you need to start considering the high end, HDR, NDR, XDR technology, especially. And again, this goes back to your PIs. What does the customer need? What kind of performance do they need? And that's where we tailor the solution to that end. So, but some centers just they go all out, and they get it all done at the beginning. So they sort of create a catch-all solution. But there's a way to get these higher performance InfiniBand networks if you can find co-investors within your faculty or within your administration to upgrade the fabric to your systems. So it's all about relationships. How you develop your relationships with your PIs, with your administration. And so, but it's doable. I've seen it happen several times. Okay, so let's talk a little bit about storage. What we use is we use a DDN parallel file system, and we have home directories set up for the users. We also have scratch space for them as well, and we can also allow them to use some of the scratch for their projects, for their especially if it's too big, because what we do is we set up quotas on home so that you can only put so much in there. It's primarily set up for just where your apps live, where your code lives. We try to encourage folks not to store their output, their data in home, and so that's part of the hygiene of being a user on a cluster. But we do allow people to use a lot of scratch for a lot of their research data storage, as well as their their output. But I have to send nasty grams now and again when folks pretty much overstay their welcome, or they put too much data, and then it takes away from the other users. So that's something that we have to contend with at all times. Storage types, there are traditional file types. Okay, so how big do we allow for home? I think it's no more than 20 gigs. And then we start sending that. The system will actually not allow them to add any more to the system until they bring it down. Yeah. So we have storage types. There are traditional file systems. Those are the types from the very beginning. Those are our spinning disks. There are also parallel file systems that involve hybrid flash and spin. And then there's the storage systems that are now being touted today as the solution. And these are the flash parallel file systems. They're pure flash. The only reservation I have on that is what are the lifespans of the flash drives themselves, and compared to, like, say, spinning disks, how will that affect our investment in just going pure flash? So, and maybe warranties will answer that question, because when you do many reads and writes to flash systems, it basically degrades its performance, or it shortens its lifespan. And so it's a question that I have, actually. So I want to explore that even further as we get to know more about this technology of pure flash storage. There are resource managers and schedulers that are used on supercomputers. The resource manager oversees the available resources of the cluster, and the scheduler determines what runs where. For example, Slurm. I saw somebody mention Slurm in the comments. Torque, Moab, PBS, and LSF, and not all of these are free. So again, this goes back to the question make or buy, depending upon budget, depending upon the size of the organization. Some organizations think it makes sense if they don't have enough staff, or at least enough people who are familiar with open source, to just buy the solution. And we'll see an example of that in just a minute. Okay, HPC software. We had this little talk just a second ago. There are general use software out there that come bundled in. You know, all of your essential compilers, your essential tools that you need to use in the Linux environment. And then there's the field-dependent HPC software that our PIs are going to ask us to install. You know, everything from, you know, Gaussian to lamps to different versions of R, things of that nature, updated packages for MATLAB. So we service all of those. That is what we do. But I understand that some people, I think I remember a talk yesterday where someone mentioned they had over 600 applications installed on their machine, which is pretty much standard, right? If you're going to service a campus, yes, you should have several applications already, and they should be identified based on the discipline and the college that it's serving, you know. And so, because each discipline has its own particular sets of applications that they use, and sometimes there's overlap. The physicists and the chemists use CFD, and mathematicians like to use Mathematica and things of that nature, and MATLAB, of course. But again, when you're in HPC, you begin to learn what is it that the majority of your users use. And so it's nice to see them smile when they find out that you already have their app installed on the cluster. You know, especially a lot of the new postdocs and the newer students, when they're trying to do their work and they ask the question, oh, by the way, do you have this version of R installed? Yeah, we do. And so that they're very pleased. And that's what we, and it makes us all look good, right? Especially when a new professor or a new student shows up and says, do you have X installed? And we're like, yeah, we do. And they're just pleased because they know that we know what their requirements are before they even told us. And that's the kind of level you want to get at in high performance computing when people ask about your, you know, what is it that you do and what are the applications you have. We're ready already with our hands filled with solutions, and that's where you want to be when you're doing HPC software support. There are other HPC components. For example, we need to benchmark our resources, especially new resources. We want to be able to know what the upper limits are for compute. So we ask the question, are we running at peak efficiency? Security and logs, they help users and sysadmins understand our CI behavior. You know, why is it that a process is going out of control? Or maybe we could understand why a piece of software isn't working correctly. And so all that information gets captured by the logs. Security, monitoring utilities such as Tenable and Linux Defender. It's very good to help us harden our systems and to look for vulnerabilities, especially in the age of open source software that reaches its end of life, or somebody out there finds a 0-day vulnerability within one of these components. So it's good to have Tenable to help us look for holes in our system, to help us look for vulnerabilities, and then Linux Defender to keep out the malware people, to keep out the people who would hold us for ransom. So that's something that one should consider. Backup systems, you should have those. It should answer the question, is our data safe? So backing up research data is very important, because if you think about it, it took a lot of time, effort, and money to create that data. So basically that data is money, and we have to keep it safe. It's an investment. Cooling systems. So we need to find the balance between the amount of cyber infrastructure and the ability to keep it cool. And so that's always going to be a challenge, and you have to work with your data center personnel. It's also good to have thermometers, temperature monitoring. That's always good. Backup power. There's always the thunderstorms that happen here in Texas. So you definitely need to have some sort of backup to protect your machines, to protect your resources. And then licensing. This is something that you need to stay vigilant on, and that is sometimes you'll have a piece of software that the license runs out on, but your customer needs to get the job done like in a couple of days, but the licensing just expired. So the key is staying on top of your licensing before they expire. And with that, I'm certain everybody here has experienced that before, where somehow the MATLAB license can no longer be accessed because it expired. It happens. So the key is being vigilant and creating a schedule to monitor your licensing. So let's talk a little bit about the traditional HPC cluster and how they're set up. So like you saw earlier in the Ansible deployment slide, it basically defined, what's, the part of the clusters that we can deploy to. Here you can see in this diagram the compute nodes, the master node, login nodes, the interconnects that we have here, and the parallel file system. And then there's a separate file system which is used for home and storing your data. And so this is basically the configuration that you see here for a standard HPC cluster. In this case, I just put in Open HPC because that's what we use at UTD. And it's open source, and we can redeploy something like this, a cluster this size, in about a day. Then there's a commercial, which goes back to the whole make versus buy. And I think this is where Amazon and Google are starting to get a really strong foothold in this niche. And that is building a commercial cluster, either locally or on the cloud. In this case, you can use Moab on your local machines, and it's commercial. So it's basically a cluster in a box. And it allows people to do a quick installation as well. And again, I'm not here to bash anything. I think if it works for you, this is great. If it works for you, this is great. But you need to know that this is a possibility, especially for smaller shops who don't have the DevOps personnel to develop something like you saw earlier. So this is a cluster in a box, and it will save you time and effort for development. But you're locked into a licensing agreement, and then you have to continuously buy this. So, but there's perks in this though. That is the self-service portal. You can actually log in to a website and you can submit jobs. And there's also an admin dashboard that will let you know about the health of your resources, what's going on in the job queue. Licensing manager. So did MATLAB expire or not? If it did, then from the command line, we can fix that. Network manager and all that is all monitored and can be virtualized on a dashboard. So you can see how Moab is very, it's very attractive, and it allows, it creates a lot of value from the first day. But again, it's this whole make versus buy. Do we have to keep buying the software to keep our cluster running? And if you want to do Moab, the answer is yes. And then there's virtualized HPC clusters. There are both open and commercial cloud. And I'll talk a little bit about the open. So if y'all remember from Exceed, they had a cluster called Jetstream. And in Jetstream, you can set aside some nodes where you can then create an open HPC cluster, and you don't really have to pay for it. You just have to get your allocation set up. But that's going to change later with the coming of the next version of Exceed. But so that's why I put this here. So there are opportunities for an open cluster. And then there's commercial cloud, such as, Amazon, Google, Nimbus. There are several cloud providers that are showing up. And as you can see here, all these are virtual machines. And so you create your virtual networking appliances. You have your virtual storage, your virtual interconnects, and you basically are doing what you do in real life. You create a front end, you create a login node, and then you have compute. And then you can use whatever scheduling mechanism you decide to use. You can use it. Works just like a normal cluster. It's just that it's in the cloud. It's someone else's computer running in a data center somewhere. But again, this is perfect if you don't have a machine room, right? If you don't have a machine room, this is a perfect solution, especially if you have a university and you have PIs, but you just don't have a machine room. And let me tell you something, machine rooms are expensive to build. I lived through one build. It was amazing. We lucked out though. A long time ago, it was going to be a movie theater, but then it got retrofitted to become a machine room at Texas Tech. So nobody wanted it, so IT division got it for a steal. So we lucked out. But again, if you're going to build a machine room, those things can get very expensive. Okay. All right. So let's see what else we have here. So let's have an interesting discussion about time. How long is a trillion seconds? Well, as you can see here, 1,000 seconds ago was equal to about 17 minutes. It would take almost 12 days for 1 million seconds to elapse and 31.7 years for 1 billion seconds. Therefore, a trillion seconds would amount to no less than 31,709.8 years. So HPC provides this amount of compute time and more with each technology breakthrough. So when I mean everybody in HPC, we've provided well over 1 trillion seconds of compute time to, solve world problems, to solve engineering problems, to solve medical problems. And so that's one of the best things that ever came from high performance computing. I mean, we built a virtual time machine where we can save compute time using all of our capabilities built into high performance computing. So this slide in itself, I think, is pretty profound. Then we have opportunities, though, to improve this statement. But before we do that, let's talk a little bit about how high performance computing was able to do all this computing. Well, first of all, as we know, computers store numbers in a floating point format. They're called floating point numbers. A single instruction, like addition or multiplication, is called an operation. And so HPC speed is measured in terms of a floating point operation per second, or flops. And so when we're measuring the performance of a supercomputer, we have two indices. One is the Rmax, which is the maximal impact performance achieved, and the other is R peak, which is the theoretical peak performance. And so as you see here on the right, there's a little table that this basically talks about the operations per second. And then the next slide will talk about a little bit about how this can scale. Okay, but as you can see here, you can see the evolution of high performance computing, where we were measuring things in kilobytes, then megabytes, then gigabytes, then terabytes, then petabytes, and then exabytes, right? And in terms of compute, kiloflops, megaflops, gigaflops, teraflops, petaflops, and exaflops. So this is sort of like a 20-year, a walk down memory lane at the top of this scale. And as you go down, we approach 2022. So the CPU clock frequency in gigahertz is generally the speed of the system, and the clock speed of the system in cycles per second, and this is hertz. And the number of floating point operations per cycle. For example, a 2.6 gigahertz processor has 2.6 billion cycles per second, or 16 floating point operations per cycle, which if you multiply that by 2.6 billion equals 41.6 billion flops, which is 41.6 gigaflops, as you can see. And the speed is getting better as we make bigger supercomputers. And speaking of bigger supercomputers, here's the top 500 history. For example, we have the Laura Mijitsu numerical wind tunnel from 1993, which was 124.5 gigaflops. Then Roadrunner from Los Alamos was 1.026 petaflops. And then IBM Summit in 2018, which was 122.3 petaflops. And then the next one for 2022 is Frontier, which is at the Oak Ridge National Lab. And it's an exaflop supercomputer. It focuses primarily on materials and energy, and also to identify new materials, new power sources, and new power storage devices. It also has a health area, including a lot of research in drug discovery and treatment efficacy. And protein docking and other things that are important for drug discovery are on the system, but it's the people who made this, they say that it's really a broad array of application areas. And they said that before they turned the machine on to production, that 24 different scientific applications were already ready to be used on the system on the first day. And these span a really wide array of different science domains. And why is that? Because we all know in high performance computing what our customers use. So when we build a new supercomputer, we make sure that we take the apps from the old supercomputer and of course make sure they're modernized, make sure they're the most recent ones, and get them on the new supercomputer. So that's service. They create the world's fastest supercomputer, and it's already ready to run applications in pretty much any field on day one. And that's the type of service we all need to provide our customers. And so Oak Ridge National Lab gets an A. HPC in the cloud, again, we spoke a little bit about cloud computing. The pros, the cost is low, especially if you use Jetstream, for example. They're easy to build. If you can run Ansible playbook, you can deploy it just as well as you could on the cloud. The cons, if you go the commercial route, there are some costs, and they can add up rather fast, especially if you don't monitor usage, or you have a sort of a pay-to-play kind of model. Costs can get out of hand really quick. And then there are compliance issues. Is the solution secure? Is the data safe? And also vendor specific. Not everybody is going to give you the same deal. So you can't say, I went to Amazon and I got a deal over Google, because maybe Google will give you a deal over Amazon. Again, it's vendor specific. So it's about relationships and about how much you're willing to invest in the cloud. Again, it's harder to track on the institutional level, especially if other departments, other colleges have their own agreements with the vendors. There's nothing preventing them from doing that. So yeah, and this has happened in the past too with high performance computing software, especially if you have departments that have smaller servers and they have licenses, and then they come to you and they say, well, do you have this app? And we're like, yeah, we do. And so they're paying for a license and I'm paying for a license. And then we're all paying for a license that only one group should really pay for. So again, we have to have better communication with our scientific community. And so we have to make sure that, let's see, we have some questions. This may sound silly, but do the pros outweigh the cons? It depends if computing is bursty. Okay, yeah, so it looks like somebody already answered the question, thanks. And then the next thing I want to talk about is quantum computers. So transistors are already at the atom size, so what's next? So the use of quantum mechanical phenomenon, such as superposition and entanglement, can be used to perform computations. Now, right now, we're still in the formative phase. I would say we are, with quantum computing, where we were say in 1977 with the microprocessor. We can do some really interesting things with it right now, but we're still working out the kinks and getting generalized computing to work on a on a quantum computer, which will basically it will be the new supercomputer once we get this thing developed where we need it to be. Again, how they operate, they use quantum states versus just ones and zeros on a standard computer. So using quantum algorithm, we can solve complex problems beyond the capabilities of a classical HPC system. So you all may have heard of a term called quantum supremacy. Quantum supremacy means that the job can only be completed on there I go again, can only be solved on a quantum computer. And these are normally time-bound problems. So what would have taken, say, 9,000 years to do on a supercomputer, a quantum computer can do it in seconds. So these are the types of things that we want to take advantage of. And of course, we've been using these things to break encryption. So quantum computers have pretty much thrown encryption out the window. Of course, there's new research on quantum encryption. And so there's a lot of hot research topics in quantum computing. So what can we do as users of high performance computing? What can we do to help facilitate quantum computing for our users? And also, how can we incorporate it into our own centers? Well, there is a development toolkit called QuizKit. And what this allows you to do is it allows you to build or design quantum circuits. You can run these on virtual systems or run it on a VDI node. Then you can compile the circuits for specific quantum service, such as a quantum system or a classical simulator. And then you can run it on your supercomputer. Now, it's not going to have the same performance as a quantum computer, but what you're doing is you're running a simulation, making sure that the code works locally. And then when you feel confident, then you can submit the actual job to a real quantum computer, and then you can take advantage of that. And so what this does is it reduces your costs for development on a quantum computer. So you're not wasting dollars using a quantum computer to develop your application. You can use your supercomputer to develop your quantum application and then submit it that way. And if anybody's interested in some free quantum computing and just a how-to, there's a little link at the bottom of this slide. You can follow it. You can install it on a VDI node on your cluster. Let your users get access to it. Your physicists will love you for it. And it's free. And once people feel confident, then they can talk to IBM or Google to get some free time on their quantum computer. There's another company that I had been working with called D-Wave. They will also give you free time if you are interested in research, or if you have a class, if you're teaching quantum computing. And so this is what you get here. You can run this in Jupyter Notebook. So I had mentioned this earlier. If you're running Jupyter Notebook, you can do quantum computing on your supercomputer. And so this is actually on the QuizKit website where you can download these examples. And then it will then create, this is an example where you are creating a quantum circuit and you're doing something called transpilation, which is interesting because, you know, when we're in computer science, we like to compile things. Well, in quantum computing, you do something called transpiling, and you create this interesting task graph on the left. Well, it's a DAG, actually. It's a DAG graph. And this basically shows the quantum functions of a quantum program. So if you are interested, please, by all means, look into it. I firmly believe this is the future of high performance computing. At some point in the future, we're going to have the ability to submit jobs directly to a quantum computer from our clusters. Kind of like how we access the CRAN in R. You know, how we all submit our jobs and we need to use our library, so we just call it from the internet. I think this is going to be the next step in the evolution of computing, where instead of installing accelerators, the accelerator lives somewhere out there and we can access it virtually, and it'll be quantum. Okay, so again, Exceed had it's coming to an end, and it had 6 systems. It had Stampede 2 at TAC, Comet at San Diego Supercomputing Center, Bridges at the Pittsburgh Supercomputing Center, Jetstream at Indiana, and then the Open Science Grid. I worked on that for several years, and then Ranch at UT Austin. So what is happening now is the Follow-on to Exceed program will be instituted this year, September 1st. So the National Science Foundation has awarded $52 million over 5 years, and has awarded sub-awardees to facilitate this. And so it's going to allow people to use the resources just like they did in Exceed, but the funding will continue through April 30th, 2027. And these are the different tracks involved. And so you have Pittsburgh Supercomputing Center in track 1, University of Colorado Boulder in track 2, which is the user services team. Track 3 is the Connect Operations and Integration Service team, which is NCSA. And then the Monitoring and Measurement Service, which is the State University of New York at Buffalo. And they do the monitoring, measurement, service model, and data analytics framework. So if you're interested in using these resources, this should come online later this fall, and you can start applying for access to the Access program. Okay. Well, I think we've reached the end of this here. Do we have any questions from the group? There were a lot of good questions during the talk, but I have some questions for you, like how do you compute? Are you planning any new deployments, and are you exploring new technologies? And also, what are your users asking for the most? So, and that's the $100 question, and it has Henry's face on it. Questions? How many compute cycles can you get with 100 Henry bucks? Well, with the way inflation's going, probably infinite. Okay, GPUs. Okay, so users are asking for GPUs. San Diego Supercomputing Center is using composable. So yeah, the questions are coming in. Let's see. So there was a question asking if we use Slurm. Yes, we are using Slurm. And another question, Sagnik asked, where was I at Texas Tech? The answer is yes. That's where I came from. Let's see. Oh, and Henry says that I ran out of time. So, all right. All right, Henry, well, I'll hand it back to you then. There's a lot of very good questions, by the way. It looks like there are some people who want to put together their own clusters. And if you have questions, by all means, please email me, and I'll be happy to get you in the right direction.
All right, let me turn off the recording.